Plasma is ionized gas which contains electrons and positive ions. But every ionized gas is not plasma. Plasma is defined as a quasi-neutral gas consisting of charged particles that are electrons and positively charged ions which exhibit collective behavior. So here two terms are important. One is quasi-neutral and other is which exhibit collective behavior. Quasi-neutrality means 4 dimensions greater than a particular dimension, its overall charge is 0. This is meaning of quasi-neutrality. And by collective behavior, it means that the motion of charged particles must depend not only on the local conditions but also on the state of the plasma in the remote regions as well. In plasma, motion of charged particles give rise to electric and magnetic fields which affect the motion of other charged particles far away. A fundamental characteristic of plasma is its ability to shield out electric potentials applied to it. Shielding distance is measured in terms of a quantity called dBi length, and dBi length lambda d is equal to under root epsilon 0 kt upon Ne square. Here epsilon 0 is permittivity of free space, k is Boltzmann constant, and E is charge of electron, T is the absolute temperature, and N is the charge density. If we put the values of these constants epsilon 0, k and E, we find this lambda d equal to 69 under root T upon N in meter. This lambda d, which is known as dBi length, it is a measure of shielding distance, the distance up to which the electric potentials applied to the plasma are shielded. Now this is one of the plasma parameter, dBi length, lambda d. Now if we draw a sphere of radius equal to dBi length, it is known as dBi sphere, and number of charged particles in a dBi sphere is given by Nd, number of charged particles in dBi sphere. We write it as Nd, and dBi sphere is the sphere having radius equal to lambda d, having radius equal to dBi length. So in this sphere, in this dBi sphere, number of charged particles will be n into 4 by 3 pi lambda d cube. 4 by 3 pi lambda d cube is the volume of Debye sphere, which have radius lambda d. And if we multiply it by small n, that is charge particle density, number of charge particles per unit volume, then n multiplied by this volume 4 by 3 pi lambda d cube will gives the number of charge particles in this Debye sphere. If we put the value of lambda d, this comes equal to 1.38 into 10 to the power 6 t to the power 3 by 2 and to the power minus half. So these are two plasma parameters. One is Debye length lambda d and other is nd, number of charge particles in the Debye sphere. Debye sphere is a sphere having radius equal to lambda d. Now we see what is the criteria of plasma. A criterion for an ionized gas to be a plasma is that it must be dense enough so that Debye length lambda d is much smaller than the dimension of the system, that is L, to ensure collective behavior. So to ensure collective behavior, we must have lambda d Debye length much less than L. L is the dimension of plasma. This is the first criterion for an ionized gas to be a plasma. This is the condition for the collective behavior. Now we have defined number of charged particles in Debye sphere nd. It is n into 4 by 3 pi lambda d cube. Second criterion is related with this nd, and this nd must be much greater than 1. Number of charged particles inside Debye sphere should be much greater than 1. And the third criterion is related to collisions of charged particles with neutral atoms. If nu is plasma oscillation frequency and Tm is the mean time between collisions, condition for the gas to behave like plasma is nu Tm should be greater than 1. Nu is electron plasma frequency. Tm is the mean time between collisions, and this nu multiplied by Tm must be greater than 1. So these are the three criterion for an ionized gas to be a plasma. Lambda d much less than L, nd much greater than 1, and nu Tm greater than 1. Now we consider the wave phenomena in plasma or plasma oscillations. Plasma is electrically conductive fluid composed of electrons and positively charged ions. Due to its electrical conductivity, a plasma couples to electric and magnetic fields. In plasma, there are negatively charged electrons and positively charged ions, and these are moving. So there is electrical conductivity because electrons and positively charged ions are moving inside the plasma. And if these charged particles are moving, they will produce electric and magnetic field. Waves in plasmas are an interconnected set of particle parameters and field parameters which propagates in a periodically repeating fashion. These waves in plasma can be classified by the oscillating species. There are two species, electrons and positively charged ions. So, we can classify the waves inside the plasma by the oscillating species, whether it is electrons or it is positively charged ions. The waves related to electron oscillations have radio or optical frequencies, and these are related with electromagnetic waves propagating in the plasma. Example is Langmuir wave. The waves related to ion oscillations have lower frequency and known as magneto-acoustic waves or acoustic waves influenced by the presence of magnetic field. Example is Electron wave. So, according to oscillation of species, we can divide the oscillations in plasma in two categories. One is oscillations of electrons and other is oscillations of positive ions. Due to oscillations of electrons, low frequency, high frequency radio or optical frequency waves are produced. Example is Langmuir wave. And due to oscillation of positively charged ions, low frequency waves are produced, which are magneto-acoustic waves. Magneto-acoustic waves are acoustic waves influenced by the presence of magnetic field. And example is Electron wave. Rapid oscillations of the electron density in plasma are known as plasma oscillations or Langmuir waves. By neglecting the thermal motion of electrons, angular frequency of such oscillations is given by omega Pe equal to under root 4 pi Ne E square upon m. Omega is angular frequency and Pe is for electron plasma frequency. E for electron, P for plasma. So, if the rapid oscillations of electron density in plasma, then the waves are of this frequency, which is known as electron plasma frequency, omega Pe, and it is given by under root 4 pi Ne E square upon m. Ne is electron density, number of electrons per unit volume, E is charge on electron, and m is mass on electron. So, this is the frequency of the waves produced due to electrons, due to change in electron density, due to oscillation in electron density. It is known as electron plasma frequency. Here Ne is number density of electrons, E is the charge on an electron, m is the mass of an electron, and epsilon 0 is the permittivity of free space. Electron wave is low frequency wave produced in plasma by oscillations of ions in the presence of magnetic field. The ion mass density provides the inertia and the direction of, and the presence of magnetic field provides the restoring force. These waves propagate in the direction of magnetic field. These waves can change into the magnetosonic waves when the propagation is perpendicular to the direction of magnetic field. Alpine waves initiated the field of magnetohydrodynamics (MHD), for which Hans Alfvén received the Nobel Prize in Physics in 1970. So there may be two types of oscillations in plasma according to species, according to oscillations of electron or oscillations of positive ions. Mechanism of plasma electron oscillations. Expression for electron plasma frequency. Now we want to find the expression for electron plasma frequency. The plasma electron oscillations arise as a consequence of the property of plasma to try to remain neutral. If the electrons in a plasma are displaced from a uniform background of ions, electric fields will be built up in such a direction so as to restore the neutrality of the plasma by pulling the plasma back to their original position. Because of their inertia, the electrons will overshoot and oscillate around their equilibrium positions. Such oscillations have a characteristic frequency known as electron plasma frequency. This is the diagram showing the oscillations of electrons. If by some means these electrons are displaced from their mean positions, as shown by these arrows in the direction as shown by these arrows, then since plasma have a property that it tries to become neutral, so these electrons experience an electric field in opposite direction so that the neutrality of plasma is restored. But due to inertia of electrons, these electrons will shoot out and oscillate about their mean positions. So in this way, the oscillations of electrons are produced, and the frequency of such oscillations is known as electron plasma frequency. We want to find the expression for electron plasma frequency. For this, first we write equation of motion. This is the equation of motion for electron. If electron experience electric field E, force on it will be given by m dv upon dt equal to minus EE. Mass into acceleration is force, dv upon dt is acceleration. So mass into acceleration, that is force, and force on electron is equal to minus EE. Minus E is charge on it and capital E is the electric field. So due to presence of electric field, force on electron will be minus EE, and we write this equation as equation 1. From Maxwell's equations, first Maxwell equation gives this relation del dot E equal to 4 pi rho. There is another form of this Maxwell equation, that is del dot E equal to rho upon epsilon 0. But we write this form here, del dot E equal to 4 pi rho. this is in the units where 1 upon 4 pi epsilon 0 is put equal to 1. So for epsilon 0 we write 1 upon 4 pi, or for here if we write del dot E equal to rho upon epsilon 0, in that equation we replace epsilon 0 by 1 upon 4 pi. So this is one of the form of first Maxwell's equation. In another way we can write it as del dot E equal to rho upon epsilon 0, but here now we use this form del dot E equal to 4 pi rho. Here rho is charge density, and charge density of electron rho is equal to minus Ne. Minus E is charge on electron and N is the number of electrons per unit volume. So rho, charge density of electron, is equal to minus Ne. So this Maxwell equation now becomes del dot E equal to minus 4 pi Ne. We write it as equation 2, and third equation we write is equation of continuity. This is the equation of continuity, which is del dot J plus delta rho upon delta T equal to 0. This equation of continuity relates charge density rho and current density J. J vector is current density and rho is charge density. So equation of continuity is del vector dot J vector plus delta rho upon delta T equal to 0, or since we have rho charge density as equal to minus Ne, it is charge per unit volume, charge of electrons per unit volume. N is number of electrons per unit volume, and charge on each electron is minus E. So charge per unit volume, that is charge density rho, is equal to minus Ne, and current density J is given as minus NeV. Here also minus E is charge on electron. So charge density rho is minus Ne and current density J vector is minus NeV vector. If we put these two values of rho and J vector in this equation of continuity, del dot J plus delta rho upon delta T, it gives del dot NV plus delta N upon delta T equal to 0. This we write as equation 3. So we have three equations. First is equation of motion of electron, that is mass into acceleration equal to force. Second is Maxwell's first equation, and third is equation of continuity. Now assuming a small perturbation in parameters E vector, V vector and N H, we assume a small perturbation, a small change in these parameters, such as E vector is equal to E0 vector plus E1 vector. E0 vector is its equilibrium value of electric field, and E1 vector is a small change in it, that is a small perturbation. Similarly, for V vector we write V0 vector plus V1 vector and N equal to N0 plus N1. Here E0 vector, V0 vector and N0 represent their equilibrium values, and E1, V1 and N1 represent a small perturbation in these values. If we put the values of E vector, V vector and N to equations 1, 2 and 3, we get these three equations. m into d upon dt v0 plus v1 equal to minus e into e0 plus e1. Del dot e0 plus e1 equal to minus 4 pi n0 plus n1 into e. Del dot n0 plus n1 into v0 plus v1 plus delta upon delta t n0 plus n1 equal to 0. Now we assume that change in equilibrium values that are delta E0 is 0, delta V0 is 0 and delta N0 is 0. Change in equilibrium values we assume as 0. E0, V0 and N0 are equilibrium values of E, V and N. We assume change in these equilibrium values as 0. Then these three equations now becomes, this first equation become m into d v1 upon dt equal to minus e e1 by taking small change and assuming change in equilibrium values e0 and v0 as 0. Second equation become del dot e1 equal to minus 4 pi n1e, and in third equation we have del dot n0 v1 plus delta upon delta t n1 equal to 0. In the third equation, in the first term, we have four terms. First is n0 v0, other is n0 v1 and n1 v0 and n1 v1. These n1 and v1 are small quantities. These are perturbations in and v. So, out of these four quantities, we neglect the three quantities and the remaining quantities is n0 v1 in first term of this third equation. Then we have del dot n0 v1 plus delta upon delta t n1 equal to 0. Write these three equations as equations 7, 8 and 9. Now if we assume plane wave solution in one dimension as e to the power minus I omega t minus kx, we can assume plane wave solution as both e to the power plus I into omega t minus kx and e to the power minus I into omega t minus kx. Here we assume plane wave solution like this: e to the power minus I into omega t minus kx. If we differentiate it with time t, then with t we have minus I omega. So differentiation with respect to t gives minus I omega, that is delta upon delta t is minus I omega. And if we differentiate it with respect to k, with respect to x, then it will give ik. With x we have ik. So we have delta upon delta t equal to minus I omega and delta upon delta x equal to ik. Substituting these two values in these three equations 7, 8 and 9, we write for d upon dt as minus I omega. So this equation 7 becomes minus I omega m v1 equal to minus e e1. In equation 8 we have del vector dot e1 vector, and del vector contains three components: delta upon delta x, delta upon delta y, delta upon delta z. And this delta upon delta x differentiation is equal to ik. So we write here ik for del vector, and this gives ik e1. and IKE1 is equal to minus 4 pi n1e. And in third equation we also replace tail vector by Ik, and we have Ik n0 v1, and in the second term for delta upon delta t we write as minus I omega. In this way we get these three equations for equations 7, 8 and 9. These three equations can be written as this. We write these three equations as equations 10, 11 and 12. Now by simplifying these three equations we can find the value of omega, and that will be the electron plasma frequency. From this third equation, that is equation 12, we put the value of n1 in previous equation, which gives the value of capital E1. So from equations 11 and 12 we get capital E1 equal to minus 4 pi k n0 v1 e upon I k omega. We here put the value of n1 from this last equation to the second last equation to get this value for E1. Here k is cancelled out in numerator and denominator for E1, and so we get the value of E1 from these two equations 11 and 12, and from these equations 11 and 12 we find the value of E1, that is this, and put this value of E1 in this equation 10. Putting the value of E1 in equation 10 we get I omega m equal to minus 4 pi n0 e square upon I omega, or omega square m equal to 4 pi n0 e square. Here I square becomes minus 1 and minus is cancelled out, which gives omega square as equal to 4 pi n0 e square upon m, and this gives omega equal to under root 4 pi n0 e square upon m. This omega we write as omega Pe, and it is known as electron plasma frequency. So in this way we find the expression for electron plasma frequency omega Pe equal to under root 4 pi n0 e square upon m. If we have used in this Maxwell's equation, which is del dot E equal to 4 pi rho, if we have used this as del dot E equal to rho upon epsilon 0, so we then have to replace 4 pi by 1 upon epsilon 0, and then the expression for omega Pe will be similar to this expression, except 4 pi is replaced by 1 upon epsilon 0